Okay, so now that we officially started, so thanks again for the invitation to give a webinar, and it's my pleasure to talk about positional games. And yes, as I've been talking about this topic for some while, and on various occasions, and been on various levels. I have compiled some kind of broad introduction to the field, and with just a general overview without going into too many details or getting into proofs in much detail. As we are, especially knowing that there's not too many people, if you have any questions, please interrupt me. We really want everyone to get everything. I mean, that's my hope, and yeah, I think it's not going to be also too deep in terms of what I require for previous knowledge. So I'll try to go on around things that require some special things outside of the main thread. So yeah, if you have any questions, do interrupt, please. And yeah, so positional games, the outline of the talk, or whatever we managed to cover, I will not rush through it, but yeah, that my plan is to tell you a little bit about what a positional game is and what kinds of positional games are there, and give you some of the examples that you know of positional games. And then we will talk about probably the most important kind of positional games in terms of how much it was studied and how much attention and importance it gained through the years. This is the games on graphs, playing games on graphs, in particular games on edges of graphs. And then also we'll touch upon the different types of games. This is what's called conventions usually in combinatorial game theory. There are several types of positional games, and I will mention the most important of them. And finally, I'll show you a criterion, which I think is probably with one proof, as this is a longer talk. I should have a couple of easy proofs, but yeah, as I said, it's like basically like university math required to follow, and hope we can go through it. Yeah, so let's start slow. Generally, games, when you look at games, can be split into games of defined as games of pure chance or mixed skill and chance, or games of pure skill, depending on the role of randomness, on how much randomness is in the structure of the game. And on top of that, a different partition of games is partitioned into perfect information games and imperfect information games. This is based on the availability of information to players. Do all players know everything that is to know about the game, or is there some knowledge which is available to one and not the other? And then finally, games can be also based on the order of play, defined as games of sequential information, sequential games or simultaneous games. Again, the difference is whether players play in succession or they play simultaneously. And what we will look at is what is called generally combinatorial games. Those are games of pure skill, perfect information, sequential games. In particular, let's repeat once more what is the type of games that we are looking at here. The games of pure skill, that means that there is no chance involved, like it would be in some kind of, like say, card games, where depending on how lucky you are, you will get good cards or bad cards, or like flipping a coin or throwing dice. So pure skill means that there is no randomness involved, no random events determining anything. And then perfect information, that means there is no hidden information. Again, if you're playing cards, you may see your cards that other players don't see. We don't have that. Everyone sees everything, and all the information is public. And finally, sequential games, this is an important distinction, where if you have simultaneous moves, this is going in the direction of what we know as this branch of basically economy originally, where like you have a lot of math theory, which is called combinatorial game theory. Sorry, not combinatorial game theory, where you have equilibria, probabilistic strategies, etc., etc. In contrast to that, combinatorial games are sequential games, and you have one player playing after another. And these games are much more like tame and analyzable, mathematically analyzable, and also more fun to play as a like a game of if you want to play it for fun. On the other hand, these simultaneous games, just one more remark, they are better for modeling real life situations, because in real life there's not too many situations where you have opposing entities who wait for each other's turn to play. Usually opposing entities play simultaneously or as soon as they manage. And yeah, so we are looking at combinatorial games. These are the bold ones, or these emphasized structure that I just talked about. And moreover, this is a particular kind of combinatorial games, positional games. So I will define that in a second. But before that, I'll give you an example. Tic-tac-toe is a well-known positional game. So I'm sure you all know it. It's like either called tic-tac-toe or X's and noughts, etc., etc. And the board of the game, or what we call the board of the game, these are these 9 little squares. And then the winning sets are the triples. So the triples would be, I'll draw a little bit. So these triples, etc., etc. There's 8 of them, 3 here and 3 here, and 2 diagonal ones here. Altogether 8 of them. And they define what is called the winning sets, how to win the game. In what sense? Well, the players, we call them red and blue, or we can call them X and O, or X and naught. They alternately claim unclaimed elements of the board, so they can put a mark where there is no mark, or claim that element of the board. And then the outcome is determined based on who claims a whole winning set first. So as you know, in this game, you take 3 in a row, you win if you're first. And there is a draw. A draw is possible. For example, this here is a draw position. So this game has ended in a draw. That means there is no 3 in a row of any player. Okay, that's tic-tac-toe. And why did we define it? Because actually this structure here, or this description here, actually corresponds to what we know as positional games in general, and what we define as positional games. Which way? So before I tell you the definition of a positional game, just one remark. If you have any combinatorial game, so really literally any combinatorial game, to determine the winner of the game, actually, it is enough to look at the game tree, because we know the definition of the game, we know the combinatorial structure, we know all the possible moves, we know the game tree. And if you look at tic-tac-toe, you can define this game tree. Of course, there is more here. This is just first 2 moves. So this is the starting position. Then these are the 3. So this here are the 3 positions up to isomorphisms. Of course, there's 9 of them, but some of them look the same. 3 positions to which you can get after the first move. Then the next level is the second move, and then there is more. Obviously, here you would have more on each of these leaves. So it's a huge tree already for tic-tac-toe for such a simple game. And looking at this tree, actually, if you study it, if you apply an algorithm on it, you can really determine the winner and the strategy for the winner of the game. How is that done? Probably most of you know it, as we're dealing with games here, and many people study games in various ways. So there's this well-known algorithm called min-max algorithm, or this has several other names. What is min-max algorithm? We look at this tree. So now we are looking at the bottom part, one bottom part. So the tree is, of course, is huge. This part here is just one part at the bottom here. This is what we are looking at here. And this here is the end positions. So this is the game ended. And then the level above it is 1 move before. And also like this here already ended because you have 3 in a row, and etc. etc. So what we do is we can assign a number to each of the end positions on the leaves of this tree. We can put a -1 if the outcome is second player's win, and we can put a 1 if the outcome is first player's win. And then we can propagate this information up. What does that mean? That means that if we are in this position, that means it's first player's win, X wins, because we have 3 in a row. Then if we get to this position, then that's also first player's win, X will win. even though there's one move ahead. And then here again, this is a -1. And then if we are here, then we have O is to play. If O plays here, he wins. If he plays here, he loses. Then optimal player will play this way, in this direction, and win. So that means that we can propagate information applying min and max. So if there is a -1 on this level, then the information will be propagated. And then we do that, apply minimum on when it's second player's turn, and then apply maximum when it's first player's. And then note, if you propagate this information, as I said, in the whole tree all the way up, in the end, in the root of the tree, you will have an outcome. As we know for tic-tac-toe, there could be a 0 as well. 0 would be a draw. There will be a 0 here, and you will know that there is a this game is a draw, and you will have a strategy for each player to force a draw. What is the strategy? Literally look at the place where you're at the moment, and just go in the direction of applying the maximum. So if you're here and your position is 1, where will you play? You will play in the direction of a 1. That's a simple strategy if you have this huge tree analyzed. So essentially that's an algorithm to tell you who is winning. But still, if you have a complicated game, this is obviously not an efficient way to determine the winner, and that's why we study the games to find the outcome in some more efficient way. Yeah, this is what I just said. And then now let's define the positional game. So in full generality, a positional game is defined by the board. This is a finite set. And then a set of winning sets. This is a collection of subsets of the board. And altogether, these two define it. So how does it look like? In full generality, you can have a set, like a base set, which you call the board. And then you would have some subsets of this. These would be the winning sets. And this, sometimes we call it the hypergraph of the game. If you're familiar with what a hypergraph is, then you know that this is a hypergraph. Essentially, it's just what is a hypergraph? A vertex, a collection of elements and some sets on it. Literally this. So we call it the hypergraph of the game. And this is the structure of essentially any positional game. And then on top of that, how is the game played? Well, the game is played by 2 players who alternately claim unclaimed elements of the board. That's kind of obvious. So again, like in tic-tac-toe, what is claimed cannot be claimed again. So you have to claim from the unclaimed elements. And then until everything is claimed. Who wins? And this is where different conventions come into play. We have several conventions, several ways of defining who wins the game. And here they come. First is what we call strong or maker-maker games. This is like tic-tac-toe. The player who claims a whole winning set first wins. And also a draw is possible. And this is, as I say, in tic-tac-toe. And then there is probably the most important and most studied convention of positional games, maker-breaker games. These are sort of similar in definition to the strong games, but there is one crucial difference. The first player wants to claim a whole winning set, maker. But the second player, breaker, just wins if maker does not claim a winning set. That means breaker just wants to prevent maker from claiming a winning set. Breaker does not have a power to win by claiming a winning set. He just wants to prevent maker from claiming one. And then this game has 2 outcomes, essentially. Makers win and breakers win. There is no draw possible because as soon as maker is not winning, breaker is winning. So these 2 are equivalent. And then 2 more to mention are the sort of misère version of these 2. What does that mean? That means that there is strong avoiding. We flip the winning criterion into the losing criterion. Essentially, and that's what in this, let's say the concrete statement. So the player who claims a whole winning set first loses. This would be strong avoiding game or avoider game. So you don't want to claim the winning set, a whole winning set. And then a draw is possible if no one claims a winning set to the end of the game. And then again, there is a weak version of this. avoider, enforcer games, then again we have a symmetric the naming as well as roles of players. Enforcer wins if avoider claims the whole winning set. Avoider wants to avoid the whole winning set. Enforcer wants to force him to claim a winning set, and who manages is the winner. So again, there's just two outcomes: avoider wins or enforcer wins, depending if avoider claimed the winning set, a whole winning set, or not. So these are 4. There's actually some others. I will just mention these. I'll stop here, but yeah, there are more. And just one small remark: if you write something in the chat, I will not see that. So just if someone sees something, if someone is not willing to ask questions by voice but by typing, I will please let me know, as I'm not looking at Zoom. Anyway, yes. Let's give another example. So now that we define these conventions, the important thing to realize is that let me put the slide back. So you have this structure, and then with any of these conventions, you can play the same game. So you look at the game, you can play strong maker, you can play maker breaker, you can play strong avoider, you can play avoider enforcer on the same structure. So basically you have four different games, 4 different combinatorial games. So we can play tic-tac-toe in the second convention, the maker breaker convention. So what is the game? The game now is maker wants to make 3 in a row, and then breaker wants to prevent him. And let's play. So we have this board, and then if maker plays here, then breaker can play, for example, here. And then if maker plays here, then breaker there is this threat here. So breaker has of maker, the breaker has to play that to avoid losing in the following move. But then if maker plays here, then there are 2 threats. There's a threat here and a threat here simultaneously. And obviously breaker cannot do anything to prevent the loss of the game in the following move. So breaker, for example, plays here, and then maker plays here and maker won. And note that 3 in a row of breaker would not matter. So breaker just wants to prevent this. As he failed, it's maker's win. Maker wins. I mean, in this particular gameplay, and it's not hard to argue that maker can win in any case, or the breaker cannot prevent maker's win. So tic-tac-toe is a draw if you played strong game, maker, strong game, but it's a maker's win if you play maker against breaker. Another example worth mentioning, hex. Game of hex was invented simultaneously by Hein and by Nash. And it's a well-known game, and many of you surely know it. It's a hexagon or rhombus of hexagons, and players alternately put red and blue or claim hexagons, and they're aiming to connect their respective sides. So blue has 2 sides here, coast if you wish, banks, and red has 2 sides here. And obviously, like in this game, we have that this is not very visible. Yeah, the blue won because there is a connection of blue and blue. So you want to connect your codes, and that's how you win. Obviously, a connection of blue is automatically denying a connection in red because these 2 are not connected anymore. But actually, there's what we know as hex theorem. Hex theorem is winning is equivalent with not losing. That means the opposite is like if there is no blue connection, then there must be a red connection between the red codes. So if there's no blue connection, then you can look at the blue part connected to the left one, if the left one and right one are not connected, and follow it. And next to it, there will be a sequence of red that essentially connect the top and the bottom. So this is called the hex theorem, and then this is a game which cannot end in a draw. And then you don't quite see this, I think, right? But it says that hex is a positional game, and why is it a positional game? Actually, it's not straightforward because one thing that is not allowed in a positional game that currently we have defined is that winning sets in blue and winning sets in red are not the same thing. But we can be actually it's defined as a make or breaker, or it can be defined as a make or breaker game, where winning sets are all red connections. So these are the winning sets. And then it's maker who wants to claim one of those. And then breaker would be the blue player who just wants to block all of those. If breaker manages to put one mark on every path, red path from top to bottom, that means he prevents maker from connecting top and bottom by red. And automatically, by this hex theorem that I just told you, automatically preventing red from connecting top and bottom automatically gives you a sequence of blue by this theorem. So if red did not manage to connect up and down, then automatically blue has a sequence of blue hexagons from left to right. So this means that this is a make or breaker game, and then as it's a positional game, we know all the things that we know in general for positional games that hold for hex. And then one important remark that's also general. There's not that many general statements about positional games, but there are some actually. This is a common thing also for the combinatorial game theory and game studying games in general. That there are not that many. Very quickly things get out of hand and become too hard to analyze. But one general criterion or a couple of general approaches are easy to state, and I will tell you what they are. One of them is strategy stealing. What is strategy stealing? Well, let's prove this and demonstrate what strategy stealing is through this statement. The statement is the following: in every strong game, so every strong game, the first player can guarantee at least a draw. What does that mean? What does that mean? That means that first, so there is no second player's win. So if you have, say, if you have tic-tac-toe, the original tic-tac-toe, the outcomes are first player's win or a draw or second player's win. But essentially, this theorem says that this is not an outcome. And for any game of this sort, any strong game, any maker game where the first player to claim a winning set wins, there cannot be the one where second player has a winning strategy. And we will just show that. So take any game which is played in the strong sense, who is the first to claim a winning set is the winner, and suppose that the second player has a winning strategy or a contradiction. If this is the case, if the second player has the winning strategy, this strategy can be seen as a set of rules, what to do, how to play as second and win. For every position of the game, mid-play, you have instructions what to do in this case, where to play. This is the strategy. And suppose it exists for the second player to win the game. Then what happens is the first player can actually steal this strategy, or if you want, copy it, take this as a book or whatever, and get one as well. And then the first player will do the following: play an arbitrary first move and sort of forget about it. And then pretend to be second. He will pretend to be second and then use the same strategy, same winning strategy, and then play according to it. So what can happen? So let's say this is the board of the game. So we have our board of the game and some winning sets, so on. And then what the first player is doing is he's playing here, and then arbitrary move, and then forget about it. I will put it in brackets. That means this is a move the first player played but forgot about it. Then the second player plays somewhere, responds as the game goes on. And then the first player will look at the strategy S, and we look at what is the strategy S saying as a response to this first move here. What is the response to that? Say this is the response. And he plays here. Then blue again plays somewhere. Then red looks at the strategy and again plays somewhere. And say the strategy now says play here. What will red do? Red will uncover this one, the previously forgotten one, and play another one somewhere and forget about it. And this is what's written in this third bullet. And continuation, eventually, because this is a winning strategy for the second, without the forgotten move, red will win. Red will be the first, a second in this made-up game, will be the first to claim a winning set. And obviously, this forgotten move will not change anything because red can only have a winning set sooner if you look at the forgotten element. So altogether, this implies that the first player also has a winning strategy. So if the second player had a winning strategy, then first player can steal it and using it also win, which is a contradiction, implying that this assumption was wrong. The assumption the second player has a winning strategy is not possible. And that means that we have our theorem proved. So this is called strategy stealing. It's a very powerful argument applied a lot, many situations, and we can also apply it in positional games. In particular, we can apply it combined with Ramsey argument. What is a Ramsey argument? A Ramsey argument is the following. Suppose that every two coloring of the board contains a monochromatic winning set. What does that mean? That means something that holds for some positional games and some boards of the game, some hypergraphs of the game, if you wish. If you have your board and you look at it, and somehow you know that no matter how you, let's say this is a winning set as well, or something like this, that doesn't make sense, but let's say this, okay? No matter how you red-blue color the board, no matter how you do it, there will be one red or one blue winning set. This particular structure is not the case. So this one does not have a Ramsey property because I just colored it without a monochromatic winning set. But there are some that have, and I mean this is if you probably many of you know, there's a whole Ramsey theory studying hypergraphs like this. What structure should various collections of sets have so that no matter how you two color the elements, there will be a monochromatic set. So if this holds, then automatically you can apply a strategy stealing. Why? Because if every two coloring of the board has a monochromatic winning set, that means when you end the game, when you finish the game, the board is two colored, somebody is winning. If you look at the game tree, there is no draw. Every end position, if you look at the end positions in the game tree, this is either a -1 or a 1. So if you apply min-max up and propagate the information down, this here will be either 1 or -1. So there is no draw. So if you know that for some reason, one way or another, for example, from graph theory, if you're playing on graphs, etc., if you know that your board has Ramsey property, then you know that there is no draw. And then what can we conclude? For example, together with strategy stealing, we know that first player wins the strong game. So if you play a strong game, so strong game again, this is the first convention that we define, like tic-tac-toe. Whoever claims the first to claim the winning set is the winner. So if you have that, we know that there is, so like we had again the situation, 3 possible outcomes, draw and second. We earlier on previous slide, we eliminated the second player's win for all games, but if it has a Ramsey property, if the game G has a Ramsey property, then we also know that the draw is not possible. So if the draw is not possible and the second player's win is not possible, the only thing that remains is the first player's win. We know automatically that the first player wins in the strong game. And then also, if you have make-or-breaker game, we know that maker wins in the make-or-breaker game. That's also, if you want to repeat the argument, if you're wondering why is that, you can repeat the argument of strategy stealing. If breaker would be able to win, that means breaker would be able to prevent maker from claiming a winning set. But if the game ends and the breaker as the second player prevented maker from claiming a winning set, that automatically by Ramsey property means there is a breakers of a winning set. And that means that the second player has a strategy to claim a winning set by just blocking the first. And that's a contradiction, because the first player can steal this strategy as first, as we saw on the previous slide. So every maker breaker game played on the Ramsey property board is a maker's win. Automatically, we know that. An important thing to point out is that this is not a constructive result. We know that maker wins. We know in this case, we know that first player wins in this case, but we have no idea how to win. We know that there exists a strategy for first player to win. We know there exists a maker strategy for the maker breaker convention of the or version of the game, but there's no way to determine the strategy. And actually, as we saw in Hex, not by applying this, but just looking at the Hex theorem, we know that Hex is the first player's win, just like that. Just from this what we derived here. We know that if second player would be able to win, the first player would actually play a random, or not random, arbitrary move, hide it, and just do the same as what the second is doing, just mirrored in his direction, and then win as well. So that's of course not possible. So second player never has a winning strategy. And actually, Hex is an interesting game to play anyway. One reason is that, first of all, we don't know what the winning strategy of first player is. We don't know that at all. And secondly, there is an additional thing. There are tournaments of Hex, and actually usually there is one thing to overcome this unequal situation. One way to do it is to just add in the beginning of the game possibility for the second player after the first move of first player to switch sides. So in the Hex game, first player wins. First player plays. So you have your Hex board. First player plays somewhere, and then the second player decides at this point, does he want to switch sides or not? Does he want to continue with this being his first move or not? So that if the first player plays a move that is really good, then the switch will happen. If he plays a really bad move, that switch will not happen. That's bad for him. So there are some moves which are sort of borderline good or bad. And this is how you somehow equalize chances in Hex for the practical play. But that's not particularly. It's just an interesting curiosity. Yes. So I actually see your raised hands, Lisa. So do you want to?
Yeah. Yes, I have a question concerning the role of the player who is maker and the one who is breaker. I mean, because when you play X, you're switching the role. I mean, sometimes you are defending your line, and sometimes you are building your line. So from what I understand, you are switching role from being a maker or being a breaker. Does it make sense, or is there something that I didn't understand?
Yeah, that's a good question. So yeah, essentially, Hex in its nature is like a strong game. So I will go all the way back just to make sure that I'll just what I'm talking about. It's a bit back, but I'll try to be fast. Yeah, here. So strong games, these are like tic-tac-toe. This is like whoever is first to claim the whole winning set is winning. Both players can win by claiming a winning set. And this, in nature, this is what's happening in Hex. It's like two players both want to win, but they also want to simultaneously block the opponent from winning, right? So essentially you're doing two things simultaneously with the same move, right? So you're trying to build your structure, and you're trying to ruin your opponent's structures at the same time. And this is really the essence of how these kind of games, strong maker games, are like. On the other hand, in maker breaker games, situation is much more tame, much more sort of structured, because each player has just one thing to do. Maker wants to create a winning set, and breaker is just blocking. That's why maker breaker games are much easier to apply, much easier to relate to other and analyzing. Yeah, also. But yeah, so let's go back now to Hex. And now, what actually your question? Yes, that's here, about here. Yes. So in hex, essentially you're right. It's a strong game in nature, but it turns out because of hex theorem, it can be seen, it can be defined as a make or breaker game. This is just a consequence of the hex theorem. So even though blue wants also to build and block, right? So blue has this in the definition of the game. Blue wants, how was it probably from left to right? Blue wants this whole blue, but also wants to prevent red. By hex theorem, blue just can block red. It's enough that he blocks red. If he manages to block all red paths, if the game finishes and there is no red path connecting up and down the red coast, automatically by hex theorem, we know that there is a blue path from left to right.
Yeah.
And because of that, it's actually a make or breaker game, if defined like this. And then actually it could be one way to make it much easier to analyze, because you can just say, okay, can blue prevent red from connecting up and down without caring about blue connections left and right? And yeah, so essentially then it is a make or break game. So I hope I answered your question with the introduction.
No, yes, perfectly fine. Thank you very much.
No problem. Yeah. And I have one more example. We're slowly switching towards the games I promised, the games on graphs. So let's play make or breaker triangle game on K6. So how does that look like? Well, the board is the edge set of the K6, complete graph on 6 vertices. And then the winning sets are all triangles. So here we have a K6 with white edges. Edges are not claimed. They're neither red nor blue yet. And then players are, this is an example of the gameplay. Red plays here, and then blue plays, for example, here. And then if red plays here, this is a threat. So to prevent this, blue has to play here. But already when red plays here, cannot avoid losing in the following move because there are 2 threats, and blue cannot block. And again, note that it's make or breaker. So playing this here and making a blue triangle does not make a difference. So this was a gameplay example of an easy or like straightforward red's win. So red would in the following move claim a triangle and win. And actually it is not hard to prove by analyzing case analysis that maker can win, but we can also prove it by this developed theory, a little bit of theory that we developed in previous slides. How? Well, maybe I can actually ask if someone has an idea of how to show that this is a maker's win. So if you like, what we did was we introduce the strategy stealing argument combined with Ramsey argument, and this is what we want to use. And yeah, so right. So what is the conclusion here? Well, K6 is Ramsey. K6 is Ramsey. If you look at the edge set of K6, it's the first example usually. If you look at if you introduce any Ramsey theory, the first example is like if you two color edges. Sorry, if you take K6 and you take all edges and color them either red or blue, you cannot avoid claiming a triangle. So you can try, but there will always be a triangle in the end. So if you finish and color everything, there will be a monochromatic triangle, either red or blue. And that's Ramsey property. I will not finish this. But as K6 has a Ramsey property, we automatically know that it's maker's win by Ramsey and strategy stealing. And then actually I will skip this. Actually, what I already said, this is just like, I don't need to read the details of the slide. Actually, strong games because of these. So we had in connection to Lisa's question, I'll just comment a little bit. Strong games are hard, and actually one of the things that is in the root of that hardness to analyze these games is this twofold role of every player. So like players simultaneously block and build, and this is very hard to to kind of capture in any kind of argument. And this is why there are so few results in strong games. And to strong games, generally, most of the questions to strong games are actually open. And I will just mention a little bit about strong games that we know. One thing that is easy to understand and like tame and like tic-tac-toe generalizations. What is a tic-tac-toe generalization? Well, n-square game. This is the game where the board consists of n by n collection of squares, or like a big square divided into n by n squares and n squared little squares. And the winning sets are n in a row squares, n on a line. And then we have, I hope the definition is clear. The ordinary tic-tac-toe is 3 squared. So you just have 3 by 3 network, our grid. And then we know already it's a draw. We discussed that in detail, and of course everyone knows that already. But let's look at 4 squared. 4 squared is also, it's not hard to also conclude that it's a draw. You can do it by case analysis or by somehow, playing with it for a minute, and you will see it's a draw as well. And actually for the 5 square game, we already have what we call a pairing draw. There is a special argument here that works, which gives us a draw by what we call pairing. So what is a pairing? What does it mean, a draw? First of all, let me discuss that a bit. In a strong game, so it's strong, tic-tac-toe is like the ordinary tic-tac-toe. Strong, that means whoever wins first. And we already said in a strong game there are 2 possible outcomes: first player wins and a draw. There is no second player's win. So we're just wondering for each game, is it the first player's win or is it a draw? So 3 square is a draw, 4 square is a draw. And what I'm playing here is that 5 square is also a draw. And not only it's a draw by pairing. And this diagram should help you understand why it's a draw. And let me explain what the diagram says. The diagram says whatever the first player X plays, say here, if X plays here, you look at the mark. Maybe I shouldn't have done it so bold. Let's say it like this. You see this mark, the green line. The green line marks the horizontal line. And there's another one in this horizontal line. If you look at any winning line, there are 2 marks that correspond to the direction of that line. For example, if you look at this vertical line, there are these 2. I will erase this, but let me just point. So if you look at this horizontal line, there are these 2. If you look at this diagonal line, there are these 2. So let me just remove them. But every winning set has 2 in the same direction. And then you do pairing. What does it mean? That means if your opponent plays here, you're second, you will play the other one. Then your opponent plays here, for example. That's the diagonal one, you will play here as second. So you want to show that second player has a strategy to draw. So this is essentially what second player wants to do. It's not second player's win, but that's the best second player can do. So second player is fighting for a draw. And he can do a draw. And it probably is clear now why. Because every winning set has a pair in it. And if you look at the winning set, this winning set will not be completely red. Why? Because the first time red plays one of those 2, say this one, the opponent will claim the other. So this will not be completely red. That holds for every winning set, so it's a pairing draw. And that's a stronger thing than just having a draw. And you may wonder, could it be that there is a pairing draw for 4 squared? Do we have a pairing draw? Well, we cannot have a pairing draw there. Why is that? Well, simply because like counting how many elements do we have? How many winning sets do we have? We have in 4 squared, there are 10 winning sets. And there are 16 elements of the board. And why is that automatically giving us there is no pairing draw? Because for the pairing draw, we need 2 elements per winning set. So here, like for every winning set, 2 elements. And of course, you cannot share the same pair cannot cover 2 winning sets because winning sets are lines, and lines don't have two elements in the intersection, 2 different lines. So 10 winning sets, we need 20 elements to pair for a pairing draw on 10 winning sets. And we don't have that. We have 16. So there is no pairing draw. No pairing draw in 4 squared. But this pairing draw can be generalized for anything above. So if you look at n squared, if you would add 1, if you look at 6 squared, you just have 3 new winning sets. This one, and the new diagonal. And you can pair them with new elements. So let's add new pairing. This one, you pair with this one. And then these 2 are you pair, and these 2 you pair. And this pairing is automatically a pairing for 6 squared. So this 6 squared is a pairing draw. And you can continue that and show that n squared is also a pairing draw. So essentially we have the 2-dimensional tic-tac-toe generalizations figured out. They're all a draw. Actually, they're not all a draw. What happens with 2 squared? 2 squared, that's homework actually. Figure out who wins in 2 squared and 1 squared as well. But with this, we analyzed it. So it's everything is on. Let's switch to 3D. What is 3D? 3D would be a natural extension. So you have n to the 3 or n cubed. It's a cube. So n by n cube, and then again n in a line on a line are winning sets. How does that look like? Well, let's look at 3 cube. So that's a cube, 3 by 3 by 3, and winning sets are either parallel to an edge, or diagonals of a side, or these space diagonals, big diagonals of a cube. So there's 3 types, and then you can look at how many of those are there. It turns out there are many winning sets, this many of the straight ones, and these ones like the diagonal, these like second type, and then 4 of the third type, because there are 4 diagonals. The big diagonals, there are 4 of them. So that's the number of winning sets. And then you ask the same question: who wins in this game? And let's first look at the 2 cube. That's again an easy example, because you have cube that is 2 by 2 by 2. And again, if the first player plays here, then obviously second player cannot do anything to not lose in the second move already. But already 3 cube, that's more challenging to analyze. And it turns out that's an interesting case, an interesting example again of the application of what I told you about, strategy stealing and Ramsey argument. It turns out that 3 cube is having a Ramsey property. So that cube, I'll go back. This cube with these, no matter how you 2-color the little cubes, there will be either a completely red winning set or completely blue winning set. And again, I'll write this again. If that is the case, then because of the Ramsey property, draw is impossible. Automatically, we know that 3 cube is the first player's win. And then 4 cube, that's already, it's an interesting game to play. That's a result of Patashnik from 1980. Computer aided proof where actually in this year that was quite rudimentary, also like a pioneering work almost, and like one of the first proofs by computer in combinatorial games. And this is a 3D printed 4 by 4 by 4 tic-tac-toe. And yeah, apparently blue one here. Here is 4 in a row. Ugly. I'll just probably remove this. Yeah, here, 4 in a row. And the interesting thing is that already for 5 cube, we don't know. It looks like an easy and innocent game, but computer analysis apparently is or all attempts so far have failed. So if you're a fan of that, you like analyzing. Obviously, the game tree is already huge here, but here actually analysis by computer already with computers from 1980 worked. But if you compare 4 cubes and 5 cubes, that looks like just one step up. But the depth of the tree, if you look at the game tree, this depth is the number of moves. Essentially, the depth of the tree is going from 4 cubed, you go to 5 cubed. And that's a huge difference in depth, knowing that the size of the tree grows exponentially with that. So every additional level will give you as many moves. There are, of course, towards the end, there are less moves, but you're adding new levels in the middle, essentially. That's what's happening. And this is making the tree so big that so far any attempts have failed to determine it. This is an interesting, I would say, an important open problem to determine the outcome of the 5 cube game. And I will just quickly remark a few things about N to the D game. So just to ask, do you want me to talk for 1 hour, or what do you, that's what I understood, with questions, without questions, or, I mean, I'm flexible.
So well, I would say maybe slowly wrap it up to give some space for questions.
Excellent. Yes. So I will just mention that there is N to the D, and there's some that has been studied, and there are some important results about it. And I just want to maybe go back to tell you, yes. So I will. I mean, obviously this is a very long talk. So this is probably a 3-hour long thing if you tell it all together. And what I want to, okay, maybe I just do this. Yes, I want to sort of advertise some literature about this. So we have 2 books on this topic. One is the book of Beck. This is from 2008, and I was lucky enough to hear a series of lectures of Beck when he was writing this book. That's how I first learned about positional games. That was in 2003 or 4 or something like that, and that's when I mean, Beck is one of the pioneers and one of the fathers of the whole field, and he has several groundbreaking results in this field, along with also the early results were by Erdős, Schwatal, and Selfridge, and some others. And the book contains these earlier works, and also we have a book that so you have. So this is not. Let me see if okay. Yeah, you can download it if you wish by this QR code, or you can send me an email if this is, or you just save the QR code, print screen, or whatever. You can download the PDF if you want, and we have tried to give an introduction to positional games, and you can find it's containing some of the more recent results. Although, it's not that recent anymore. We're trying to wrap up a second edition. We'll see when that materializes, when everyone has time. We'll see when that happens. But so things I haven't told you about are, of course, there by now there are well over like several hundreds of papers on this topic. The field has gone in many different directions. So there are, of course, much more than I told you. If you want to study this field, or if you are curious, I mean, the beauty of the positional game theory, maybe one thing that I want to say that's generally a good advertisement, I think, is that it's a very simple structure. So essentially what I told you about, so you have a collection of elements of the board, and you have some sets on it. Many things in various aspects of science and real life have this structure. It's a very simple structure, what we call the hypergraph. Essentially, it is just a collection of sets. If you have that, if you have your, like, I don't know, triangles in a graph, or you have cubes on or lines on different cubes, or you have any other structure, you have a hypercube of some kind of sort. Whatever the structure you're studying, groups, you name it, many things have this structure. And especially if you have 2 colorings and stuff like that, it's very natural to look at positional games on the same thing. Just play a game instead of just coloring it offline or coloring it by an algorithm. You can ask yourself what's happening when maker and breaker would color it by playing, And actually, that's how we also get some connections between positional games or just applications of positional games in other fields that are nothing to do, for example, by creating a coloring, existence of a coloring, but just playing a game and coming up with the end position, which is a coloring. So if you have something that you would like to study, that you think, or that you are studying, that you're wondering if you can turn it into a game, or any other game that is not positional that you want to relate to positional games and maybe apply some of the theory, you can think about it. And of course, you can ask me. I'd be happy to answer your question, or if you have questions, or discuss it with you, or like quick Zoom. Just don't hesitate to contact me. I'll be happy to work with you on it and discuss it. Yeah, and that's all for me. Thanks.
Thank you very much, Miloš. Perhaps we have some time for a few questions in the audience, if you have something to ask. I saw that you had like an extra slides to show us, so perhaps it could be a course in two episodes. and yeah, well, that's just a suggestion, but perhaps you could, if you had more to say, it could be a good opportunity to continue this discussion also in September, if you wish to, or if you want to. But that's.
Yeah, I'd be happy to. I mean, as I said briefly in the beginning, I gave many courses on this, like longer or shorter. Some of these were something like 20 hours or more. So I have enough material to cover. None of this is really too heavy to be for general audience, especially on, I mean, not even on this level, but also if like say students or like graduate students already. Gave some master courses where it was like 15 hours recently. That all was, I thought it was very successful in terms of how much students could follow, and it's like it's same flavor as what you saw today, just goes on. But yeah, I'd be happy to, and if there is an opportunity to talk about it more, I'd be happy to.
I have to discuss that with my co-leader, but that's an option. Okay, so question in the room. You have anything to ask? Tiago, I'm sure you have a question.
No, I mean it was a very nice introductory talk to the subject, and I think it will definitely spawn interest in general public if we put this up. The depth can go way deeper, of course, and the technicalities and all of that. And I mean, most of the things are well-known results, and it was very interesting to have it presented and related to tic-tac-toe. And yeah, so thank you so much, Miloš.
Thank you. It's my pleasure. If you want the slides, I can send you the slides also if you want to put them next to the. I don't know if that's recorded thing is going to be. I mean, yeah. So let me know. We don't need to discuss it now.
I think it's recorded and it will be put in the channel. So we have the slides. So well, I'll let you know, but I don't think we need you to send us the slides beside. I just wanted to say a little thing about the history of X game, because I know it's well spread that it was, of course, it was invented by Piet Hein in 1942, and what is not really accurate is that it was independently invited by Nash, because you have a book which was published, I think, 4 years ago now, a full history of the hex game, and the authors kind of, yeah, so Tiago has it, and the authors kind of show that Piet Hein went in Princeton, where Nash and Gale were, and in the common room where they were supposed to play a lot of games such as Go and chess, and it is said that it's in this room, in this common room, that the game of X was created. First, not on an hexagonal grid, but then it was the hexagonal shapes that was thought. And so there is a huge probability that at some point the game arrived in Princeton through Piet Hein or through Danish students who went to Princeton for their studies and used to play this game because they knew it very well from Denmark and from the journal in which it was published, the Politiken. The name of the journal is Politiken. So this was just a historical precision
Note.
I wanted to say. But
yeah, thanks.
It's already really great to say that it was Piet Hein who invented it, because most of people say it's Nash, and which is not really true.
Well, I think it's controversial at best, and I think it's a good note to leave out there. John Nash, until his death, he said that he had come up with it, or
he said many different things.
He did not acknowledge any precedence to the game.
No.
But of course, he was already a well-established mathematician at the time, and he was of some age when he was asked. But yeah, so it's definitely controversial, or it's definitely pretty open. And I mean, 5 years nowadays, the time difference would be too much for independence, for sure. At that time, maybe still some sort of independence, or some, yeah. Maybe inspired.
Yeah, no, I didn't say that he was. Yeah, I think inspiration came at some point, and like the Danish students, and it is an option. Okay, let's say.
I definitely think we should take things away from the Anglo-Saxonic narrative and put some emphasis on Piet Hein.
Okay.
Yeah, I'm glad that he was listed first now. But yeah, I did not know. Yeah, thanks for the details. I don't know that much. I have a book, a copy of that textbook, but I somehow read parts of it, but not that much. Now I'm tempted, and I also revise my slides to be more cautious. I'll put some question marks around, so then I can write anything, right? Do everything and then write or did he? Question mark. That's a nice. Also some drama added. That's always good to stir up.
Yep.
Well,
Yeah,
most of the math theory was developed on those cycles by John Nash, right? So some credit there.
Yeah, some credit there as well.
Some little bit. I mean, who's John Nash?
Never heard of this guy before. Okay, well, so let's thank you one last time, Miloš. It was really, really interesting, and yeah, let's discuss about perhaps the idea of having a second round of this, because it was really nice, and I think it would be worth to dig deeper a little bit.
Of course, yeah. Thank you for listening to me, and it was a pleasure.
Great. Bye everyone. Have a nice end of the day, and nice.
And before you leave, Lisa, shall we announce the next dates? Because we'll already have a new set of dates for the
we don't
upcoming session.
We don't have anyone yet, but yes, we can announce it in September.
But we don't have speakers yet, so if anyone from the work group or some inspired speaker wants to step up, there's definitely that possibility. So after a summer break in August, we'll return in September on the 23rd. That's also Monday. Then the Monday 21st and the Monday the 25th of November. So those are the upcoming dates. And so September 23rd, October 21st, November 25th.
Oh, shoot, I mixed that up. So I'm just writing to you, so that's great. I didn't make any mistake.
Yeah, we'll just leave that in the chat real quick so it's easy to follow. And yeah.
Okay.
And yeah, hopefully we will have everyone here again at those dates. We are still looking for speakers for October and September. So if you're interested, let us know.
Yeah.
Oh, and we're going to push everything a little bit further back in time. So it will be at 6 Central European time. So it's a little bit more accessible for people from from different time zones, and hopefully we'll get some more people to join.
Yeah. Not easy being an international working group.
Thank you again, everyone. Thank you, Miloš.
Thank you. Bye-bye.
Good
Thank you
summer
very
break.
much.
Thank you. Goodbye.
Bye.